So welcome back, everybody. The topic this week is our first money-body method as an approximation to the full problem. So last week and the weeks before, we discussed full configuration interaction theory in a basis. So that means that we could rewrite in a finite basis the problem as a Hamiltonian matrix which needs to be diagonalized. Now, suppose now that the space you have defined as your effective Hilbert space is a space which represents, to a very good approximation, the system you want to describe. Now, if you then can diagonalize this Hamiltonian matrix, it essentially means that you have solved the problem. Now, we are going to use this Hamiltonian matrix setup, which ideally is the exact solution of the problem, if that basis you have chosen represents the relevant degrees of freedom. Keep in mind also that in principle, the basis you're looking at is an infinite basis. So somewhere you've made some kind of truncations. And that's essentially what money-body theory is about, to find the relevant truncations, which are physically meaningful. So Hartree-Fock is now a system, represents a subsystem of equations, which we, as we discussed last time, is going to represent a specific transformation of the Hamiltonian matrix, where we zero out some specific matrix elements. So we are going to derive the equations using variational calculus. So in the beginning of the lecture, I'm going to use a little bit these slides because there are some elements of variational calculus I want to remind you of. So variational calculus, I mean, the diagonalization problem itself is also just another variant of using variational calculus. So we are going to sketch the way it's going to look like when you do this in configuration space or coordinate space, which leads to what has been called the traditional way of deriving the Hartree-Fock equation. And then we are going to set up the same equations in second quantization. And the actual recipe is a recipe where we are going to vary the coefficients of the single particle states. But I'm going to remind you of some of the basics of variational calculus first. So the aim today, as you probably have seen from the slides which I sent you, is essentially to go through the Hartree-Fock equations, which lead to a practical way of implementing them. So the equation which you will typically find in a normal textbook on Hartree-Fock theory are often given in terms of equations in coordinate space. That leads to, from a computational point of view, to less practical and less efficient equations because they involve coupled integral differential equations. Now, I'm not going to go through that, except for some brief sketches, but you will find these derivations in the lecture notes from last week. So we are going to focus on what's called the variation of the coefficients. And that will lead to a problem which we have to solve iteratively, but where we're going to diagonalize a matrix. That means that we will have tabulated the entries to the matrix, which we call matrix elements, and then we are going to set up a diagonalization problem, and every iteration is going to give us better and better coefficients, which are the overlaps between the old basis and the new basis. So that's the essential recipe. Now, then there is some nice mathematics. One of these is called Fowler's theorem, which is also something which we will use to look at the stability of these equations. So what kind of conditions do we have on the interactions which will allow the Hartree-Fock equations to be stable? So the mathematics of that is something which we will try to discuss a little bit more in detail in the next lecture. There is an exercise which essentially deals with the coupling between the basis you choose as an orthogonal basis and the Slater determinant, which you have from your chosen orthogonal basis, which we normally call a computational basis, and the Hartree-Fock basis. So these are some simple linear algebra exercises which you may find interesting or not. But one of the things I wanted to do now is just quickly remind you of Hartree-Fock theory. So it's an algorithm for finding an approximative expression for the ground state of a Hamiltonian. So it means now that we are going to have a new single particle basis, which we will typically call the Hartree-Fock basis or the mean field basis. And in this specific case, what we are going to show today is that this Hamiltonian, which is now a single particle Hamiltonian, contains what you have seen before. So kinetic energy, which is often in textbook written with a T. And then an external potential, which confines the motion of the particle. So that could be the attractive force from an atomic nucleus, where you have a given number of protons, which sets up an electromagnetic field which attracts the electrons. So that could be your U external, or it could be you setting up in a semiconductor, due to potential differences, a potential which traps, let's say, electrons or charged particles. And then there is an additional term, which comes from the setup of the Hartree-Fock equations. Then the algorithm is then to have this potential here, or this U Hartree-Fock potential, as it's often called. And with that one, you can actually show, and we are going to study that tomorrow when we look at the stability of the equations, that the Hartree-Fock equations, which you're going to solve, this expectation value gives you an energy which is larger or equal than the desired one. So this is something which we will prove tomorrow after we have gone through a theorem which is called Fowler's theorem. So Fowler's actually got the Nobel Prize in physics, and he's a British citizen who has been in the state of Washington for many, many decades. So Fowler's got the Nobel Prize for the studies of superfluidity, Bose-Einstein condensation, etc., but has made many, many similar contributions to many body physics. I've actually met him. He's a nice guy. Basically, all people are nice guys in general. There's some less nice people. Okay. We will show that the Hartree-Fock Hamiltonian is now given by this form here, where V is the potential which we are dealing with, which can be the Coulomb interaction between two electrons. It can be in the potential between nucleons or whatever. So this is basically a two-body interaction. If you have three-body interactions, a more complicated one, you will get additional terms to the Hartree-Fock part. But as we said in the beginning of the course, we will mainly stay with a one-body Hamiltonian and two-body Hamiltonians at most. Okay. So the Hartree-Fock theory, or mean field theory in general, brings in an explicit medium dependence. And the reason for that, if you go back to this equation here, you're now summing up over all the particles below the Fermi level. So you could think of these two states, Q, which is an incoming state, represents the state of a given particle. Then C is a medium, an interaction, which is set up by all the bystanding particles. So if you have atomic neon, then you would have 10 electrons if you freeze out the nuclear degrees of freedom, which is pretty common when you do atomic physics. And then the medium, as we call all these particles, which occupy all states up to the Fermi level, affects the motion of this incoming particle, and then it gets out with perhaps some modified momentum. It can have some modified energy or whatever. Okay, so this is essentially the kind of interpretation which we are going to give. So it brings in an explicit dependence on the two-body interaction, and that's normally something which we would call correlations. So the type of correlations in mean field theory arise if you're looking at fermions due to the direct term and the anti-symmetrization requirement on the wave function, which gives you an exchange term. So that's what we normally would call, even if it has the interaction only to first order in V, it is something which we would call a correlation due to the Pauli principle. And you can then say so that with the contribution from the other bystanding fermions, it creates an effective mean field in which a given fermion, this could also be a boson, so you would have a similar mean field equation for bosons, except that then you will not have the exchange term, which arises due to the Pauli principle. You would have similar terms there, and this is something which comes in addition to the external potential, which you have opted for. If you're looking at a system like an atomic nucleus, and you're interested in proton and neutrons as degrees of freedom, in that specific case, there is no confining potential, which is set up by some, let's say, additional bystanding element, because then it's the force between neutrons and protons which binds them together. This force has a very short range, which means that when they get far apart from each other, there is no binding force anymore. Okay. As I said here, there would be no external one-body potential. It's only kinetic energy plus this Hartree-Fock potential. Now, one thing I wanted to do now with slides is to give you a quick reminder of variational calculus. So I'm assuming that many of you have seen that in courses like mathematical physics, or if you've taken a course in classical mechanics and you've met the Euler-Lagrange equations, this is something which I am assuming there is a familiarity with. Okay, I hope I can do that. If not, I mean, just tell me, and then we can look at some of these equations later. So typically what you're doing then, when you look at calculus of variations, this is what we are going to apply to derive the Hartree-Fock equations. So the Hartree-Fock equations, the way we're going to derive them, we are later going to match them with a full configuration interaction picture and see what that means when we do the FCI calculations. But everything we're going to do now is going to be based on calculus of variations. So if you think back of the equations which you start with, you have an integral, and the power of these methods is that you, from looking at the energy of a system, you can derive the equations of motion. So I don't know if this rings a bell, but when you took a course in classical mechanics, you would derive Newton's equation from a Lagrangian which contained kinetic energy and potential energy. And then using the calculus of variations from that integral which you have, which then expresses the energy of the system, you could derive the equations of motions. In the same way, you can actually derive Schrödinger's equation of motion from the expectation value of the energy. So the calculus of variation is an extremely powerful way of deriving equations of motion. So it's actually much more general because you start with something which you can measure, which is typically the energy of a system, and then you set up the expectation value of that one, and from that you derive the equations of motion. So typically what you would have is something which depends on some field phi of x, which we don't need to specify here, and then a derivative with respect to some degree of freedom represented by x. So then you want to either minimize or maximize this quantity. Typically, often we end up minimizing because the energy is normally a convex function of the variables involved. Any questions? So what you would do then, when you have this equation, is to search for a variation. And this variation is typically given by the derivatives, and you're seeking after some path which would change your field phi of x by some minimal amount. And then you want to figure out whether that one, whether you can optimize that specific path. So probably many of you have encountered a problem like that one, where you have been asked to show that the distance between two straight lines, the optimal distance, no, the distance between 2 points, the optimal is just given by straight line. Have you had such an exercise in mathematics or classical mechanics? Yeah, I can see that. So this is a typical example. And the variables which we are going to have and the variation, these variables are often dependent upon each other, and that leads to the concept of Lagrangian multipliers. So when we do a variational approach or use variational calculus on a quantum mechanical problem, one of the constraints is that the wave function has to be normalized and orthogonal. So the orthogonalization gives a typical constraint on the equations. So the Lagrangian you're going to optimize then contains typically the energy of the system plus some parameters multiplied with a constraint, which in this case is the orthogonality requirement. So if you, now I'm going to go quickly through that because this is not a course on the derivation of variational equations and the Euler-Lagrange equation. It's actually just a demonstration of it. And these slides serve mainly as a reminder on variational calculus. So if you think of Schrödinger's equation, this is the expectation value we are looking at. And if you now just specialize this to one particle, which now moves in, let's say, 3 dimensions. Doesn't matter whether you do 1, 2, or 3 dimensions. And you have a normalization constraint here on the wave function. And then you have the Hamiltonian, which looks like this. So we're not going to specify anything. So I'm going just to skip here for notational convenience, the X, Y, and Z, and just write V. And then the kinetic energy is something you can then integrate by parts. And you probably seen this equation before. I don't know if you're familiar with that because you have specific limits on the integrals. So that means by integration by part, when you look at the kinetic energy term, is something which you can rewrite like this. So you get the 2 derivatives. And when I mentioned that in the equations, if you look at the equations in coordinate space, so this would be the equations in coordinate space, then you see that you have an integral here, which you would have to solve, but you also have a differential operator. So when we are looking at the equations in coordinate space, and this is one of the reasons why it's very seldom that you would use that as a recipe, a numerical recipe for solving the equations, you end up with what is called a coupled set of integral differential equations, because you have the derivative here. And that is normal from a numerical point of view. That can often be a little bit more delicate because many times you need quite many integration points to get stable and decent numerical results. So if you think of an atomic physics case, like electrons in neon, in every direction here, you would typically need at least 100 points in order to get decent results. And this is a 3-dimensional integral. So that means that you have 100 to the power of 3. So that gets quickly involved. And you will see that later when we are going to optimize the coefficients in front of the functions, we can actually reduce this to a much smaller problem, which can be tackled easily by matrix diagonalization. So when you then rewrite everything, what we have is this equation here. This is the one we want to vary. And we want this variation to be 0 of the wave function. So what we are going to do then, when we look at the variation of the wave function, we introduce this Lagrangian multiplier in order to take into account the normalization requirement. And this is the type of equation we want to solve. Then what you would typically do then is to use the Euler-Lagrange equation here. And later we will also see why you can separate the complex conjugate and the non-complex conjugate part of the equations when you now take the derivative with respect to either psi star or psi. So these are the Euler-Lagrange equations in 3 dimensions. And I'm taking the liberty of assuming that this rings a bell. And when you apply that to that equation, so what you would have then, if with this equation, you take the derivative, and that gives you simply this term here when you take the derivative. So that means inside this integral here, you have to obey this equation here. And that's nothing but Schrödinger's equation. So from the Euler-Lagrange equation and variational calculus, you get back Schrödinger's equation. And you started with the expectation value of the energy, and that gives you the equation of motion. Obviously, you have assumed that the kinetic energy looks like this, which is a central part of quantum mechanics. But if you do it classically, this will just give you Newton's equation of motion. And I guess you probably have seen that as an exercise. Okay, so this was my quick reminder of applications of variational calculus to a simple system. Now we are going to look at how this looks like when we go to a many-body system. So you can identify the Lagrangian multiplier as the energy of the system, and this is nothing but the standard Schrödinger equation. And the variational approach discussed here that provides a powerful method for obtaining approximate solutions to the waveform. Okay, so the method we are going to look at before we now switch back to the whiteboard, so this is just to anticipate what is coming. So we are going to assume that we have a computational basis. So this could be, suppose now a harmonic oscillator, if the particle is moving in a harmonic oscillator trap. It could be a particle in a box. So you have these states, which then define your computational basis. And your computational basis here is assumed to be an orthogonal basis. Now, that orthogonal basis can be used to expand another basis. So the Hartree-Fock recipe, which we are going to look at, is a recipe where we are going to vary these coefficients. So we keep that fixed. And by varying these coefficients, we are going to get a set of equations which will involve a matrix diagonalization problem. And that is a much more efficient way of solving the equations. But before we do that, we need to do some standard whiteboard or blackboard exercises, okay? So I hope, I wanted just to have this kind of introduction so that you see the overarching picture of what is coming, okay? Any questions of what the aim is? Okay, so let's go into the nitty details. And let's set up the equations here. So what we are going to do now is to introduce a new reference state. So we have defined a reference state. So this is the reference state or the reference vacuum. I will just call it the reference state, which is given by this phi 0. And that could be defined by a given computational basis, which we have. So we're going to change that to a new reference basis, which I'm just going to call phi 0 Hartree-Fock. I could put MF here, which is just stands for mean field. But now we're going to derive the standard Hartree-Fock equations. So that means that this is the wave function we want to have. And what we are going to show, given specific constraints, is that the expectation value of this quantity here, so this is our Hamiltonian of the system, phi 0 HF, is going to be, due to the variational theorem, is going to be larger or equal to E0, which is now the exact energy of the ground state. So this is a way to target the ground state of the system. If you want excited states, we actually have to labor a little bit more. So many of these simplistic many-body approaches, like Hartree-Fock theory, density functional theory, which is a much more advanced method than Hartree-Fock theory, but it's still a mean field theory, they will target the ground state. If you want excited states, we have to add additional ways of manipulating the system, and there's something which is called equational motion methods, which we will not cover in this course. So this course is very much about targeting the ground state of a quantum mechanical system. Okay, so what we also are going to show here is that this phi Hartree-Fock, and this is part of the lecture tomorrow, is hopefully something which gives a lower energy than the one which we started with our computational basis. So we would typically have a computational basis which now defines these Slater determinants or ansatses for the many-body wave function. And this energy, sorry, that shouldn't, there was a small error here, like this one. So this should be smaller or equal to the one which we would get with a starting basis. So we are going to have a basis which now is going to be modified, and it's going to be given by this Hartree-Fock basis. And it's going to be built on these states which we have originally with some variations. Okay. So essentially, this is what Hartree-Fock theory promises, or mean field theories. And tomorrow, when we're going to look at the stabilities, you will see what kind of conditions we can put on the potentials which are acting on the system, or the interactions, which is a better word for it. So if we now look at a coordinate space variation, so essentially what we are going to use is variational calculus. That's the basic entry point. And we are going to first sketch how the equations can look like when we deal with the equations in coordinate space. As I mentioned, the final derivation is something which I will not go through in the lectures, but you find the derivations in the lecture notes from last week, essentially because this is a less practical method of solving the equations, or less efficient. So if we now just look at the coordinate space variation, so we look at a single particle state, an SP state. So SP stands for single particle state. And we are having a state phi of x, alpha. So it has some quantum numbers alpha. So this is a specific state. And this is going to be varied now to have some kind of perturbation, you may call it that, or variation, some delta alpha, so sorry, not delta alpha, but delta phi alpha of x. So this is the approach when we vary the single particle state. This will also change the many-body state. Because remember now that when we made the ansatz originally, this phi 0 of x1, x2 up to xn, and then there are additional quantum numbers, which I'm just putting as dots here. That was given by a Slater determinant. It's just as a quick reminder. So this is just a coordinate space variant. So we would have a state phi 1. So alpha corresponds to the given states which we are filling up to the Fermi level. And then we have particle 1, the same quantum number 1, particle 2. So we have particles in the columns and the quantum numbers of the system as rows. So we have a phi 2 of x1, and this goes down all the way to phi of n of x1, of phi of n of xn. So this is the kind of system which we have been discussing up and down, and this is the Slater determinant. And that single particle basis which we have chosen is an orthogonal and normalized basis. So what we have, as a quick reminder, so we have I hope you don't get offended if I just remind you of these things. And then I have a phi j of x, and this is given by delta ij. So in the variational calculus, what we are going to do then is simply to look at these variations and set in a specific way of defining this delta of phi. Now, the other approach is the variation of the coefficients. In that specific case, we are going to have a new basis, and we can put a subscript Hartree-Fock on that, but I'm going to leave that in order to reduce the convention clutter here. And this is going to be given by a sum, and we have an orthogonal basis, lambda, and the new basis is also going to be orthogonal because we're going to assume that these C's are elements of a unitary transformation. So this is an O and B basis. And this is what we call our computational basis from the beginning. And what we have is that the lambda of sigma is given by delta lambda sigma. So this is an orthogonal basis. You can then show, and this is one of the exercises which we looked at early in the semester, is that the new basis, if the C's represent the elements of a unitary matrix or orthogonal matrix, then the P's will also form an orthogonal and normalized basis. That was one of the exercises some time ago. So let me quickly also remind you after this. So this is the method of choice, which we will come back to. But let's now quickly remind ourselves of the way we put up the system. So we've had a labeling where we have states below the Fermi level, which we label by letters I, J, K, L. So then we have the Fermi level here. Now I can use colors actually. These whiteboards are bonanza of color usage. I tend to be a black and white person, so putting in colors is something which really beefs off my life here. Simple pleasures, right? So we have n here, and then we have n plus 1, and these states were typically labeled with an A. So let's suppose now we have a state here, and then we have a state here. So what we can do then, when we look at this the variational calculus, is if we now take one of these single particle states. So what we are going to do then is that this single particle state, which we started with, which is a phi of I of x. So I is below the Fermi level. This is something which we now are going to transform into a modified state where we have an n of I. So this is not to be confused with the number of particles. This is the normalization constant. So we are going to make a new state, which is now a linear combination of phi ix, the original one, plus a mixture of a state above the Fermi level. So we're going to look at this as a linear combination of two different states. And obviously this phi of A of x is going to be orthogonal to phi of I. Okay? So that's a basic assumption which we are putting in here. So the change now, which we are going to look at, this change of phi of I, is going to be given by this parameter. So I actually went a little bit fast here. So let me just put an I here. So that's the change of I. This is going to be given by some parameter eta times one of the states above the Fermi level. So we're going to assume that eta is a small number, and A is obviously larger than the Fermi level. So we are bringing in a mixture of states above the Fermi level. So they can have the same symmetry. So that means the same type of quantum numbers, but the spatial part will be typically orthogonal to the spatial part of the state below the Fermi level. So if you're thinking of atomic physics, this could, for instance, be a 2s state in beryllium, and this could be a 3s state above the Fermi level. And you could then look at the 2s state having a smaller mixture from the 3s state. Okay? So what happens then is that if I look at my normalization constant, I'm going to normalize this wave function. That means that I want this to be 1. So that means I have 1 over n squared. That is simply going to be given by the integral here, d of x. And then I'm going to have a phi of I. I'm skipping the x dependence here. I hope that's okay, just for simplicity of the wave function, plus some eta times a phi a. This is an a multiplied with phi of I plus eta times phi of a. And this one, when we now look at it, because phi a and I are orthogonal to each other, so that means that when I look at the integrals involving this state and that state, that is obviously 0, because I have assumed that my basis, my original basis, is orthogonal. So my computational basis is this one. I'm defining a new basis, which is just a perturbation of the previous original basis. So if I do that, this is 1 plus eta squared. And if I assume then that this eta, the absolute value, is much, much smaller to 1, then we see that this n of I is proportional to 1 at linear order in this parameter eta, which we haven't defined, which is just a small perturbation of this state phi A. So that means that what I can say now is the following. So my state now, phi 0, is now going over to a new state, which I'm going to label just with Hartree-Fock here, just to distinguish it. It can be the same computational state as before, but now it has a small perturbation here. So that's going to be given by phi of h of f. And this is going to be the same as delta phi 0 of hf. So this eta in the previous case was just a constant in front of a single particle state, but we are using the same constant, although that changes a little bit, for the total many-body state. So phi 0 is a many-body state. And now I'm just, in order to just introduce the Hartree-Fock naming, I'm just putting Hartree-Fock here. So what we are going to do now, if we use variational calculus, is to calculate the energy from this state here. The E0 Hartree-Fock is obviously going to be given by a term where we have H Hartree-Fock, and this could be our original Slater determinant in the computational basis we have. And then we have phi 0 Hartree-Fock. But then we get the additional terms. So I get a term where I have this term here. And this is now going to include a state. I actually forgot a small thing here. I'm going to call this state for the perturbation here, just to distinguish it from the previous one. So this is going to be a delta phi 0. I forgot to put that one, that symbol there. H of phi 0, Hartree-Fock. And then I get plus eta, and then I have phi 0, Hartree-Fock. And then I have this one, and phi 0, delta, Hartree-Fock. Then I get the next term, which now contains just eta squared. And then I have a delta phi 0 Hartree-Fock of h, and then delta phi 0 of Hartree-Fock here. And then we assume typically that this eta is much, much smaller than 1, and we leave out the quadratic terms. So the standard approach, and if you remember back to the derivation of the equation of motion, equations for Newton's method, for Newton's equation, then you did exactly the same. And you did ignore the eta squared term in the derivation of the final equations. So what we are doing here is exactly the same which we would do if we had a Lagrangian which involved kinetic energy and potential energy. And we would typically leave out the eta squared terms because we assume that this is a very small perturbation. And we want to find the path which minimizes this integral, okay? So in principle, what we want now is to find the least action which now gives us our lowest possible energy. So what we want then is actually in the optimization. So the optimization problem is obviously to put the small changes which we have, delta H Hartree-Fock, equal to 0. And that means that we are going to collect the two terms which go like this one, delta phi 0 Hartree-Fock of H of phi 0 Hartree-Fock plus eta of phi 0 . And I should remember to put hats to show that these are actually operators. So this is a delta phi 0 Hartree-Fock. So we want to drive these equations to 0. Now, one of the things which you probably have seen in connection with these equations here, that there are actually two kind of requirements which we're putting in. So this eta is an complex object, so the real part plus the imaginary part. And 2, we have then that H is assumed to be a Hermitian operator. That means that the two equations are going to give us exactly the same result. So that means that for us, it suffices to just look at one of these equations. So that means that we could now look at eta of phi 0 Hartree-Fock, and we will see that immediately when we are going to look at this in second quantization. Then it's actually, that's where we are going to show that this is the case. Phi 0 Hartree-Fock, and this one is equal to 0. Alternatively, we can take the other term and solve for that one. So if we use that, we can then derive what is called an integral differential equation. And this is something which is covered in the lecture notes from last week. But we are not going to implement that. This is leads to, if we would like to implement that one, let's say in this course, that could easily be a project which could take at least a month. If you, on the other hand, vary the coefficients which I mentioned, this is something you can set up in the span of just a few hours and have a stable result. I'm not joking, actually. To do the integral differential equation is often, how to say, it is straightforward, but it takes time to have it functioning correctly. Okay, so let's now look at the other approach, which is second quantization, and how we could think of these changes. So in second quantization, what we have assumed is that phi 0 Hartree-Fock is now given by the product of all the states below the Fermi level. And then we have this accretion and annihilation operators. Then what we are going to do now, if we now look back at this variation which we put up, the single particle variation, what we assume then is that this single particle variation is given by some term which brings in a mixture from the states above the Fermi level. So if you're looking at the symmetries like the s orbitals, you have a 1s here, a 2s, a 3s. In principle, there's an infinity. So what you could have is that this state could then be a linear combination of many of these s states because they have the same symmetry. So if we now look at the equivalent of what we did in coordinate space, it means that now we could think of defining a variation where we create a one particle, one hole state, a new variation, which is equivalent physically with the one which we did in coordinate space, or what is misleadingly called first quantization. So we define a new variation, and then the variation now is defined as this parameter eta, which is a small change. And then we are bringing in a one particle, one hole excitation. So these are just ansatses which we are making about what the variation looks like. So there's nothing which hinders you to make it more complicated. So you could think of having a two particle, two hole excitation, three particle, three hole, etc. Except that then you're not going to get the same simple equations. So just keep this in mind, that the kind of states which we are making here could be made by you to be more complicated. More complications obviously mean more complicated equations to solve. So the benefit which we are getting here is that we are going to get coupled single particle equations. which can be solved by iterative algorithms. Okay? I'm trying, I hope you can apologize me for not moving too fast, because I want you to have with me so you can see the wood for the trees. Okay, so what we want then is to vary, and this is roughly where we stop now before we take a break. So we are going to vary this term here. And then we have H with phi0 Hartree-Fock. And this is something which we have calculated already, because this is nothing but, if we now use this equation here, there's going to be a phi0 Hartree-Fock. I have my AI dagger, AA. I have my Hamiltonian, and phi0 Hartree-Fock. And I want that one to be 0. That is something which we calculated last week. And that requirement is something which we will set up again in the next lecture. And then you will see that what happens now is that this state you're producing here is actually a one particle, one hole state. And we've already calculated that one. And we found that in that case, this is the same as A of F of I. And we want to drive that to 0. So the kind of, the equations which we get when we look at it this way is, with second quantization, gives you a very compact way of deriving the Hartree-Fock equation. Okay, we take a small break. Is that okay? I'm going to stop the recording here.